In this video, we are going to discuss eigenvalues and eigenvectors. A row matrix x1 equals 1, 3, 4, 2, or a column matrix x2 equals 3, minus 5, 2, 6, which contain ordered set of n numbers, in this case n equals 4, is called vector x1 or vector x2. The numbers here 1, 3, 4, 2, which we may denote by x1 equals 1, x2 equals 3, x3 equals 4, x4 equals 2. In case of vector x1 and the numbers 3, minus 5, 2, 6, which we denote by x1 equals 3, x2 equals minus 5, x3 equals 2, x4 equals 6. In case of this vector x2 are called components of this row vector and column vector respectively. In case of a matrix A 1 2 0 2 minus 1 1, which is a matrix of the order 2 by 3, this each row will be a row vector 1 2 0 and 2 minus 1 1. Similarly, each column will be a column vector 1 2, 2 minus 1 and 0 1. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. Now let us understand what is linear dependence of vectors. Suppose we have r number of vectors x1, x2, x3, xr. If there exist r numbers k1, k2, k3, kr, which are not zeros, all of them, such that if k1x1 plus k2x2 plus k3x3 plus so on and so forth plus krxr equals 0, then these r vectors x1, x2, x3, so on and so forth xr are said to be linearly dependent vectors. Next we will see linear combination of vectors. A vector x which can be expressed as k1x1 plus k2x2 plus k3x3 plus so on and so forth plus krxr, where k1, k2, k3, so on and so forth, kr are any numbers, then this expression is said to be a linear combination of vectors x1, x2, x3, so on and so forth, xr. Remember that this x should not be equal to 0. To understand linear dependence of given vectors and their linear combination, let us solve one example. We have to check whether the vectors x1 equals 1, 3, 4, 2, x2 equals 3 minus 5, 2, 6, x3 equals 2 minus 1, 3, 4 are linearly dependent, and if yes, then we have to express this vector x1 as a linear combination of vectors x2 and x3. Let us see how we can do that. Before that, let us first write the matrix equation k1x1 plus k2x2 plus k3x3 equals 0, where k1, k2, k3 are numbers which are not all zeros. We will substitute the values of x1, x2 and x3 in this equation and write k1 into 1, 3, 4, 2 plus k2 into 3 minus 5, 2, 6 plus k3 into 2 minus 1, 3, 4 equals a 0 vector 0 0 0 0. This we write as this 1 into k1 plus this 3 into k2 3k2 plus this 2 into k3 2k3 equals 0. Similarly, we will write for this 3 and k1 3k1 minus 5k2 minus 1 k3 equals this 0. This 4k1 plus this 2k2 plus this 3k3 equals this 0. and finally this 2k1 plus this 6k2 plus this 4k3 equals this 0. Now we will write these four equations in the matrix form. So that will be 1 3 2 3 minus 5 minus 1 4 2 3 2 6 4. This matrix multiplied by this k1 k2 k3 equals column matrix of these four zeros. Next, we will convert this matrix into a row echelon form by applying row transformations. Let us rewrite the matrix equation 1 3 2 3 minus 5 minus 1 4 2 3 2 6 4 into k1 k2 k3 equals 0 0 0 0. First, we will reduce this 3, 4 and 2 to 0, and for that we perform row transformations R2 minus 3 R1 for reducing this 3 to 0, R3 minus 4 R1 to reduce this 4 to 0, and R4 minus 2 R1 to reduce this 2 to 0. So we write the first row as it is 1, 3, 2. 3 minus 3 will be 0. Minus 5 minus 9 will be minus 14. Minus 1 minus 6 will be minus 7. 4 minus 4 will be 0. 2 minus 12 will be minus 10. 3 minus 8 will be minus 5. 2 minus 2 will be 0. 6 minus 6 will be 0. 4 minus 4 will be 0 again. 7 and 14 have 7 as the common factor, and 5 and 10 have 5 as the common factor. So our next row transformation will be minus 1 by 7 R2 and minus 1 by 5 R3. 1 3 2 0. 7 2s are 14. 7 1s are 7 0. 5 2s are 10. 5 1s are 5. Now, with the help of these 2 and 1, we will reduce this 2 and this 1 to 0. So, our next row transformation will be R3 minus R2. This 1 3 2, then this 0 2 1, 0, 2 minus 2, 0, 1 minus 1, 0. Now, this is the row echelon form of the coefficient matrix. Now, this matrix equation gives us two equations. First equation we get by multiplying this column by the first row, that will be 1 into k1, that is k1 plus 3k2 plus 2k3 equals this 0. The second equation we can obtain by multiplying k1 k2 k3 by the second row 0 to 1, that gives us 2 k2 plus 1 into k3, that is k3 equals 0. Because there is 2 here, we will assume this k3 equals minus 2t, where t is a parameter. That gives us from this second equation 2k2 minus 2t equals 0. That gives k2 equals 2t by 2, that is t. So here we got k2 equals t. Now we will substitute the values of k2 and k3 in the first equation to get the value of k1. So we write k1 plus 3, putting the value of k2, which is t, plus 2, putting the value of k3, which is minus 2t, equals 0. That gives us k1. 3t minus 4t gives minus t equals 0. That gives us k1 equals t. So we got k1 equals t, then k2 equals t, and k3 equals minus 2t, where t is the parameter. Now we will substitute these values in the equation which we have written in the beginning, which goes like this: k1 x1 plus k2 x2 plus k3 x3 equals 0. Now putting the values of k1, k2, k3 that we have found out in this equation, we get t x1 plus t x2 minus 2t x3 equals 0. Now since k1, k2, k3 are not all zeros, the parameter t is also not 0. So dividing throughout by t, we can cancel this t and we get the equation x1 plus x2 minus 2x3 equals 0. Now since k1, k2, k3 are not all zeros, the vectors x1, x2, x3 are linearly dependent, and we can express this vector x1 as a linear combination of x2 and x3 as x1 equals minus x2 plus 2x3. So this is expressing vector x1 in linear combination of vectors x2 and x3. Now let us understand what is meant by linear independence of vectors. Suppose we are given a set of R vectors x1, x2, x3, so on and so forth, xr, and if every relation of the type k1x1 plus k2x2 plus k3x3 plus so on and so forth plus krxr equals 0, then the set of R vectors x1, x2, x3, so on and so forth xr is said to be linearly independent. This also implies that the numbers k1, k2, k3, so on and so forth kr are all zeros. Then the set of R vectors is said to be linearly independent. Let us try to understand this, what exactly it means, by solving a few examples. In the first example, we will examine whether the vectors x1, 3, 1, 1, x2, 2, 0, minus 1, x3, 4, 2, 1 are linearly independent. We have to consider the matrix equation k1x1 plus k2x2 plus k3x3 equals 0. Substituting the values of x1, x2, x3, we write k1 into vector 3, 1, 1 plus k2 into vector 2, 0, minus 1 plus k3 into vector 4, 2, 1 equals a 0 vector 0, 0, 0. This we write as this 3k1 plus this 2k2 plus this 4k3 equals this 0. Similarly, for this 1 we write k1 plus for this 0 we write 0k2 plus for this 2 we write 2k3 equals 0. For this 1 we write k1. For this minus 1 it will be minus k2. For this 1 it will be k3 equals 0. Now these equations we can write in the matrix form as this 3, 2, 4, 1, 0, 2, then 1 minus 1, 1 multiplied by this k1, k2, k3 equals this 0 matrix 0, 0, 0. Now in order to check linearly independence, we will convert this coefficient matrix into a row echelon form so as to find the values of k1, k2 and k3. Let us rewrite the matrix equation 3, 2, 4, 1, 0, 2, 1 minus 1, 1, k1, k2, k3 equals 0, 0, 0. In order to make the first element 1, we will interchange first row with the third row and write 1 minus 1, 1, 1, 0, 2, 3, 2, 4. Next we have to make this 1 and this 3 zeros. So we will do row transformations r2 minus r1 and r3 minus 3r1. 1 minus 1, 1, 1 minus 1, 0, 0 minus minus 1, 1, 2 minus 1, 1, 3 minus 3, 0, 2 plus 3, 5, 4 minus 3, 1. Next we can make this 1 0. So for that we perform r3 minus r2, 1 minus 1, 1, 0, 1, 1, 0, 5 minus 1, 4, 1 minus 1, 0. Now the row echelon form of the coefficient matrix is complete. We write the equations by matrix multiplication. This first row multiplied by this column gives us k1 minus k2 plus k3 equals 0. Then second row into column gives us k2 plus k3 equals 0, and third row and the column gives us 4k2 equals 0. 4k2 equals 0 gives us k2 equals 0. Using k2 equals 0 in the second equation gives us k3 equals 0, and using k2 and k3 in the first equation gives us k1 equals 0. Now since k1, k2, k3 all equal to 0, that implies the vectors x1, x2 and x3 are linearly independent. In the next example, we are given four vectors x1, 1, 2, 4, x2, 2, minus 1, 3, x3, 0, 1, 2, x4, minus 3, 7, 2. We have to show that the three vectors x1, x2 and x3 are linearly independent, and hence we have to show that x4 depends on them. Here the procedure will be same. First we will write the matrix equation for the vectors x1, x2 and x3. That will be k1 x1 plus k2 x2 plus k3 x3 equals 0. After substituting the values of x1, x2, x3, it will be k1 into 1, 2, 4 plus k2 into 2 minus 1, 3 plus k3 into 0, 1, 2 equals 0. This we can further write as k1 plus 2k2 plus 0k3 equals 0. Then 2k1 minus k2 plus k3 equals 0, and 4k1 plus 3k2 plus 2k3 equals 0. This we will write in the matrix form as 1, 2, 0, 2, minus 1, 1, 4, 3, 2 into k1, k2, k3 equals 0, 0, 0. In order to find the values of k1, k2 and k3, we will reduce this coefficient matrix into a row echelon form to find the values of k1, k2 and k3. Viewers are requested to apply the row transformations R2 minus 2R1 and R3 minus 4R1, and after that R3 minus R2 to get the row echelon form as 1, 2, 0, 0 minus 5, 1, 0, 0, 1, k1, k2, k3 equals 0, 0, 0. By matrix multiplication, we will get linear equations k1 plus 2k2 equals 0 minus 5k2 plus k3 equals 0 and k3 equals 0. Now this gives us this k2 equals 0 and this k1 also equals 0. Now since k1, k2, k3 are all zeros, the vectors x1, x2, x3 are linearly independent. Now we will consider the matrix equation k1 x1 plus k2 x2 plus k3 x3 plus k4 x4 equals 0. Substituting the values of x1, x2, x3 and x4, we write k1 1, 2, 4 plus k2 2 minus 1, 3 plus k3 0, 1, 2 plus k4 minus 3, 7, 2 equals 0. The matrix equation will be 1, 2, 0, minus 3, then 2, minus 1, 1, 7 and 4, 3, 2, 2 into k1, k2, k3, k4 equals 0, 0, 0. Here the prefactor is of the order 3 by 4 and the post factor is of the order 4 by 1. For matrix multiplication, number of columns of the prefactor should be equal to the number of rows of the post factor. Therefore, we have taken k1, k2, k3, k4 here, and the resulting matrix multiplication will be of the order 3 by 1, which is this 3 by this 1. Now as usual, we will convert this coefficient matrix into the row echelon form by row transformations R2 minus 2R1 and R4 minus 4R1, and after that R3 minus R2. The row echelon form will be 1 2 0 minus 3 0 minus 5 1 13 0 0 1 1. Matrix multiplication gives the linear equations k1 plus 2k2 minus 3k4 equals 0, minus 5k2 plus k3 plus 13k4 equals 0. k3 plus k4 equals 0 is an equation in two variables, so we will assign k4 equals parameter t so that k3 becomes minus t. Using these values in equation 2, we get minus 5k2 minus t plus 13t equals 0. 5k2 will be 12t, k2 will be 12 by 5t. Using values of k2 and k4 in equation 1, we write k1 plus 12 2s are 24 by 5 t minus 3t equals 0. This gives k1 equals minus 9 by 5t. Now we will substitute the values of k1, k2, k3 and k4 in the equation that we have considered. K1x1 plus K2x2 plus K3x3 plus K4x4 equals 0, which gives us minus 9 by 5t x1 plus 12 by 5 t x2 minus t x3 plus t x4 equals 0. Cancelling t from each term and multiplying throughout the equation by 5, we get 9x1 minus 12x2 plus 5x3 minus 5x4 equals 0. Now since the coefficients of x1, x2, x3, x4, 9 minus 12, 5 minus 5 not being all zeros implies that the vectors x1, x2, x3 and x4 are linearly dependent. From this equation, we write 5x4 equals 9x1 minus 12x2 plus 5x3, and hence x4 equals 9 by 5x1 minus 12 by 5x2 plus x3. Here, since x4 is linear combination of x1, x2 and x3, we say that vector x4 depends on vectors x1, x2 and x3. And that's our final answer. Even though vectors x1, x2, x3 are linearly independent, x1, x2, x3 and x4 altogether are linearly dependent, and vector x4 depends on the three vectors x1, x2, x3 which are independent. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel to get more videos of this type. Give your comments to make these videos better. You can suggest topics on which you want me to make videos. See you in the next video. Until then, keep watching Number Collage. Thank you.